Isaac Newton teaches that gravity is a force, that everything with mass attracts every other thing with mass. The larger the mass, the larger the attraction, or the force of gravity. But this theory has many flaws, so a clever human being named Albert Einstein came up with something better: the theory of general relativity. This describes gravity not as a force, but as the curvature caused by mass and energy warping spacetime, a continuum containing three spatial dimensions and a fourth, time. To help you better understand this theory, I'll show you a visual. Notice how there's no force pulling the small planet towards the big planet. The small planet is simply following the curvature caused by the big planet warping spacetime. While the theory of general relativity was a major breakthrough in physics, it still has a tiny flaw. See, general relativity describes the universe on a large scale, and in order to better understand the universe, we have to fit it into something called quantum mechanics, which describes the universe on a very small scale. This is because for quantum mechanics to be complete, it needs to contain all fundamental forces, which are basically big forces that describe all small forces in the universe. And gravity has to be one of the fundamental forces, because none of the others explain why the Earth orbits the Sun. Now, to fit gravity into quantum mechanics, we'd have to quantize it, which essentially means to subdivide it into small discrete pockets of energy. But here lies the problem. See, general relativity describes gravity as a feature of spacetime, not something that works around spacetime. So in order to quantize gravity, we'd have to quantize spacetime itself. This is a major problem because that would mean that spacetime is lumpy and discontinuous. And in order for the math in general relativity to work, spacetime needs to be smooth and continuous. And this, dear friends, combining general relativity and quantum mechanics is the biggest problem in 20th and 21st century physics.